All right, so back again. Today's topic is equilibrium. Equilibrium is obviously having to do with things being equal. But here's the way I want you to think about it. Again, I'm going to follow along with the PowerPoint, so that way there's less that I have to write on this as we're going. So you kind of just have maybe both going in front of you or the PowerPoint next to you. But there's really two basic categories for all of our reactions, okay? There are some reactions that what we call completion. Completion is exactly what it sounds like. The reaction goes and it's done. If you are combusting something, you can't uncombust it. You can't put the ashes back together and get what you started with. Kluge might find a way, but the rest of us can't. Decomposition, rusting. Those are obviously reactions where if you have A plus B, for example, once you make AB, you are done. There is no going back. Second option, reversible reaction. Your reversible reactions are exactly what they sound like. You can go back and forth between the reactants and the products. Lots of times with this, instead of just having one arrow leading to AB, you have two arrows, okay, showing that the reaction can proceed forward and backwards. Other times, instead of two arrows, sometimes you'll see it written, depending on where you're looking, like this. Other times, if people are feeling really fancy, you'll see it like with half an arrow, like that. No matter what, those are reversible reactions, okay? They are going both ways. Number one thing you guys need to remember about chemical equilibrium is that it is a dynamic process. It is not static. Static equilibrium would mean if I have a bucket and I have a line on my bucket, okay, there's the top of my bucket, and here's my line. I'm going to fill it up with water to that line, okay, and stop. Now my bucket's at equilibrium. It is full. That counts as a static equilibrium. That's not reality. That's not the way things work in chemistry. In chemistry, what things will do, they don't just go to a spot and stay there. Think about diffusion. You're spraying air freshener. It doesn't just go and then stop. Instead, it's a constant process. So a dynamic equilibrium, back to my bucket, there's my line, I would fill it up with water. But I would simultaneously have a faucet over my bucket pouring in more water, and I would poke a hole in the side of my bucket so that my bucket is draining water. However, if it is pouring in and draining out at the same rate, I'm still going to be maintaining equilibrium. I'm going to stay right at that line. That is dynamic equilibrium. And that's what happens with chemicals. Again, they don't move to one spot and stop. They constantly move but maintain that equality. So chemical equilibrium, very simply, is when your forward and reaction reverse, your forward and your reverse reaction rates are equal. So if we have A plus B yielding AB, and then AB breaking back down again, it's saying that this reaction and this reaction are happening at the same rate. It does not mean I have the same amounts of what's at the beginning and what's at the end. Chemical equilibrium is about the speed of the reaction. It's about the reaction rates being equal. And that's a very, very, very big distinction to have. Okay, reaction rates are equal. So I'm going to tell you guys a little bit of a secret. In your notes, you're going to see something called the equilibrium constant. We may or may not be learning that math in class, but I'm not worried about you learning it. So we're going to skip right over the equilibrium constant part in this video, and we're going to go straight to something called LeChatelier's principle. Or if you're missing draft, since you're at the beach with your toes in the sand, have I mentioned I don't like either one of you right now? We can call it LeChatelier's principle, because we from draft. LeChatelier's principle very simply says, if you disturb something at equilibrium, it is going to adjust to move its way back. That is common sense. If you get too cold, you're going to shiver. If you get too hot, you're going to sweat. That's what LeChatelier's principle is. Except we're not just worried about temperature with LeChatelier's principle, although that is one of the factors that we worry about. Temperature stress, pressure stress, and concentration stress. So we're going to look at all of these kind of briefly. I'm not going to go too crazy with them, just so you can get the overall idea. And we're going to start with concentration. So if I have a reaction, okay, let's say I'm going to stick with my A plus B yields AB. It's just a simple basic reaction. If I put in more A and more B, so more of these individual reactants, what do you think is going to happen to the reaction? Did you like that? I gave you time to answer. Here's what's going to happen. If I put more of this stuff in, then my forward reaction, sorry, I forgot the other arrow, my forward reaction right here is going to have to speed up. To maintain equilibrium, I have got to have all of this A and B combining to make I've got to have all of this A and B combining to make AB. I have to speed this up to get rid of all this extra that I'm dumping in there. That's called a shift right. If I were to dump more AB in there, so this time I'm dumping all this stuff in there, I'm just putting a ton of this product, that's going to increase the reverse reaction to reestablish my equilibrium. That's called a shift left. So pretty simple idea, pretty simple concept, okay? It actually happens with your sodas. If you have a nice little bottle of soda, my gosh, that's the worst bottle I've ever drawn in my life. Just blame the fact that I'm drawing with a finger. Okay, when you open the top, the carbon dioxide whoosh comes out. But before you opened the top, the carbon dioxide, I'll make it green, was actually going back and forth between the air above the liquid and the liquid itself. It was a dynamic equilibrium where it was moving around. But when I take the top off and all this carbon dioxide leaves, I'm not able to put as much back into solution again. So the bubbles leave and leave and leave, okay? And I'm having trouble reestablishing my equilibrium, and my soda can eventually get flat, okay? So that's a concentration change. The second change we'll talk about is a temperature change. Okay, temperature changes, you've got to remember that endo and exothermic are opposites. So if one thing is endo, the opposite is going to be exothermic. One takes in heat, the other releases heat. So if I increase the temperature, I'm going to add energy, so my endothermic reaction is going to go faster to use it. So if this is my reaction, okay, let's say that going forward, it's an endothermic reaction, and going backwards, it's an exothermic. So it takes in heat to make the AB, it releases heat to break it back down. When I add energy, when I add heat, add temperature, I have got to do something to get rid of that extra energy. So that means I am going to increase the speed of my endothermic reaction to use that extra energy. So we say that it favors the product. Whatever you're moving towards is what you are favoring. Third thing that affects LeChatelier's principle is going to be pressure. Okay, and this is really only about gases. You got to remember that pressure means their molecules are colliding into each other. So we're going to keep this really, really simple. If I have dropped the volume of my tank, okay, drop the volume, that means I have increased the pressure. So that's affecting everything. That's affecting my A, my B, and my AB. Everything now has more pressure on it. So it's not just one or the other, but the system still has to adjust. So what happens is it is going to favor the reaction that produces the least molecules. Okay, we will favor the reaction, that's what RXN means, that produces the lowest amount of molecules. So let's think about this. A plus B yields AB. If we look at the forward reaction, A plus B making AB, I am making one molecule. That's all that is. That is one thing right there. The reverse reaction is AB breaking down as A plus B. That's making two molecules. So if I want to favor the reaction that produces the least, I am going to favor this reaction right here. With a pressure change like that, whatever favors the least is what I'm going to do. And for the record, it is possible to have a situation where you have, we'll do a double replacement reaction here. AB plus CD yields AC plus BD. In that case, ain't nothing good, okay? And it actually will not adjust itself at all. So there's your overview of LeChatelier's principle and equilibrium. Hope it helps a little bit.